Hi, my name is Ashleigh Henning. This is my Lab 5 about the falling slinky. In this lab, we were analyzing a provided video to analyze the motion of a slinky that is falling. We are measuring the observed motion of the stretched out slinky being dropped from rest, with hopes of being able to predict the motion of the slinky using both experimental and computational models of the data. In this situation, our system will be the slinky, and the surroundings are everything else, such as the hand and the earth. The key physics principles in this situation are Newton's second law, where we are able to relate both the velocity and the position in order to the forces acting on the object. Here we define that F net had the force of the weight as well as the drag force while the object was in motion. The slinky force was really only applied as a tension force while the object was at rest, and in this situation we understood that the F net of the slinky was 0. For our experiment, we had our initial conditions where we knew that the mass was 0.25 kilograms. Our calibrated initial position was right here. Our initial velocity was 0 on all three terms, and we started at time equals 0. Then we had our observed results where we obtained this graph here. Here we can derive that the forces acting on the object, per our definition, were primarily in the y direction. Because the object starts at rest, we see that the displacement that is over here is nothing, but when the hand lets go, there's a non-zero net force acting on the object in the y direction. This caused the ball to accelerate while approaching the ground. For our computational model, this was where we had our predicted motion of the slinky. We started by defining our initial conditions. We had the same initial mass of 0.25 kilograms. The ball's position was defined as well as the initial velocity. We had a time start at timestamp equals 0, but we increased with each iteration at a delta t of 0.001 seconds. We defined the constants of the forces acting on the spring, including the acceleration due to gravity, the j hat, which was used for our gravity, and then we derived the proportionality constant for drag force to be 2.6. Then we created a computational model to iteratively predict the motion. While time was less than 1 second, we knew that the force net was the sum of the force of weight as well as the drag force. Then we used the velocity and position update equations derived from Newton's second law to predict the motion of the object. And then with each iteration, we updated the time. Here is our primary results of this experiment, where we had our computational and our experimental results. As you can see, the graphs of the two look slightly different. However, it's important to note that with our experimental model, from 0 to about 1.4 seconds, this is when the object was initially at rest, when the man was holding it, and the only forces acting on the object was the force of the slinky, as well as the force of the weight. However, we did not account for this with our computational model, and so from 0 to 1 second, we are really looking at an extension of right here. As you can see, there's fairly linear relationship between the forces acting on the object and the position of the y position throughout time. Thus, it can be analyzed that we predicted the motion of the object computationally and experimentally. While the experimental positional analysis considered for the amount of time that was at rest, the computational model considered only when it was dropped. However, both indicated that there was a non-zero net force acting on the object, resulting in the displacement. In this situation specifically, we can understand that since the force of the weight was acting in the negative y direction and the drag force was in the positive y, and that the position was moving in the negative y direction and accelerating in this direction, that the F net was that the force of the weight was greater than the drag force, which is what caused for the object to accelerate as it went down. Thank you so much for watching.